This is called the decay rate. Where you almost always see this is radioactive decay. And the idea of radioactive decay is we have these unstable elements. They're unstable because, well, typically because they have too many neutrons. And it kind of makes the nucleus heavy. If you've taken a chemistry class or a physics class, you already know this and you know it better than I do. But the idea is you have this element and it's unstable because it's wonky. There's extra stuff. Wait, you're supposed to have this many protons and this many neutrons and this many electrons. And how many neutrons do you have? Well, I have 5 neutrons, and so I have an extra one. Well, doesn't it make it a walk? It's like having a pebble in your shoe. Or carrying a suitcase. You got 2 suitcases, and one is really, really heavy, and one's really, really light, and you end up limping crazy, and you finally say, you know what I'm going to do? I'm going to move stuff from one suitcase to the other. Hey, and what's this in here? And you throw something out. And that's the radioactive decay, is you decide, I'm getting rid of this pebble in my shoe. I'm getting rid of this extra thing that's heavy in my suitcase. I'm getting rid of this neutron. And you emit it. And sometimes as an alpha particle, sometimes as a beta particle, sometimes as a gamma particle. And all of these particles are made of subatomic pieces, sometimes neutrons, sometimes something else. And you kind of want to stand out of the way, because they're tiny, but they're moving wicked fast. And this is how you get radiation poisoning. So I was standing close to this uranium. Yeah, you got to stand near a lot of uranium. Plutonium, though, that's a killer. No, don't breathe it. But you could eat it. You could put it in a sandwich and eat it. You wouldn't want to. Iodine is just, it decays so fast. These particles are coming out so fast that if you accidentally ingest iodine, and why would you? Because you're near the site of a nuclear explosion or a nuclear accident. And there's radioactive iodine in the air and you're breathing it, or it's landing in your food and you're eating it. Well, iodine in your body only has one place that needs a lot of iodine, that's your thyroid. And so the radioactive iodine goes to your thyroid, just like any thyroid. That's why they iodize salt, because it goes to your thyroid. So it goes to the thyroid, and if it's radioactive, it's emitting all these particles, and it just kind of cooks your thyroid, right? While you're sitting in the chair, it just burns it up. And you won't feel it, but suddenly you're really tired all the time because your thyroid isn't producing the metabolic hormones it needs to. Yeah, that is why they iodize salt. If you accidentally get radioactive iodine, and you do because it's in the air, your body says, oh, I don't need it. And you pee it out, you poop it out. You don't keep it because your thyroid's already full of iodine. It doesn't need any more, and your body's smart that way. So that's why they put iodine in salt, just to save your thyroid from radioactive problems. But anyway, radioactive decay. So here's the formula. I'm going to show you the book version, just because I have to. It's in my contract. No, it's not in my contract, but I have to show you, and then I'll tell you the smart way to do it. So K is a positive, it's the rate of decay, and this is the formula. Here's the Gary version. I don't like memorizing extra stuff for a special situation. Gary, that's exactly the same as growth. Decay and growth are opposites. Yeah, it's because when I think of a decay rate, I think of it as being a negative. Right? The amount of uranium is going down. Well, that's a negative to me. So you can do it either way you want. Somehow or other, this exponent needs to be negative. And I say that because time's always positive. The only way you can get a smaller value is if the exponent, e to the something has to be negative. And you can do that by taking a positive decay rate and then multiplying by a negative. Or you can just say, look, the decay rate in my mind, it's negative, and so you have a negative times T. How long until half of the radioactive material is gone? So understand what this is. The idea of radiation, it's a statistical thing. This is really interesting from physics. So you have a uranium atom, and as I said, it's unstable. It's got a rock in its shoe, and it's limping dreadfully. And it really wants to toss that rock away, Well, when, right? And you've been in this situation where you have a rock in your shoe and you think, well, I'm going to walk up to that bench at least. And you decide to walk a little farther, and then you get there and you think, well, it's shifted a bit. I guess I'm okay. I'm going to go a little more. And then you think, oh man, it's really, really bothering me. Oh, but there's nowhere to sit down. This is too crowded. I can't do it here. Yeah, sometimes you do and sometimes you don't. And when do you? It's hard to predict. And so it's impossible to predict because it's a statistical thing. I have no idea when this particular atom, single atom molecule of uranium is going to decay. But if you give me a million or a billion or a bazillion molecules of uranium, I can tell you, after such and such an amount of time, this percent, there's a rate of decay. And you can't tell which atom, but yeah, it's kind of like death, right? There's a death rate. Yeah, death rate, that's decay. So you look at a population and you say, okay, here's 1,000 people. Of these 1,000, how many will there be in 5 years? Well, I don't know, but I can almost guarantee that it's less than 1,000. Well, there's some rate at which people die. And you can't point and say, see Fred right there? Oh, he's a goner. I mean, you don't know. You can predict, but yeah, I mean, seriously, you don't know. So the same way with the radioactivity. But this thing, how long until half of the radioactive material is gone? This is called the half-life. And here's what you do. In order to find the half-life formula, we need a formula with half. And so start with this, right? And we say 1/2 of P sub 0 equals P sub 0 e to the negative kt. And you say, well, divide both sides by P sub 0. Whatever you do to the left, do to the right. You get 1/2 equals e to the negative kt. I'm running out of room, so I'm just changing colors. You take the natural log of both sides. What are those? Those are inverses. And so you end up with the natural logarithm of 1/2 equals negative kt. Earlier I said, pro tip thing to notice is that if the thing you are taking the logarithm of is less than 1, it's a negative value. Well, the natural logarithm of 1/2 is a negative value. I'm going to divide it by negative k. That's kind of awful, isn't it? I think that's awful. How about if I do it this way? Is that better? Well, it's still ugly. We have a law of logs, right? So 7 times the logarithm of something is the logarithm of something to the 7th power. So a negative logarithm of something is the logarithm of the something to a negative 1 power, right? And so this ends up being the same as the natural logarithm of 2 over k equals t. And what do we say? I got to find a space for it. Usually written, and you're thinking to yourself, this is the doubling time formula. Yeah, but k is negative now, right? Yeah, k is negative. So it's exactly the same formula for doubling or half-life. Why is half-life important? Because of radiocarbon dating. We're in chapter 5, section 6. Here's our recap. What was this? Exponential growth. The formula was P of t equals P sub 0 e to the k t, where k is greater than 0. And we also had, another thing. We had a thing called the doubling time. And the formula for that was that t, capital T, and why not a little t? Because this is a doubling time. It's a particular time. It's a thing we want to know. Doubling time is t equals the ln of 2 over k, or k equals the ln of 2 over t. Because sometimes they'll tell you the one, sometimes they'll tell you the other. My money has to double in 4 years. I mean, it just has to. What interest rate do I need to find? That's how I would use this. I have my money at 4% interest. How long until I have twice as much? Because I'm itching to spend it. That would be this formula. And this is the formula for exponential growth. You recall that P sub 0 is the initial population. Okay, now for something totally new, totally different. This is called exponential decay. And where it comes up is in things like radioactive materials. Let's see the formula and then we'll talk about it. P of t equals P sub 0 e to the negative kt. K is greater than 0. I don't know, I have to pause for a second. I think this is stupid. Why don't you just make K negative and then you have the exact same formula? You don't have to memorize two things. Yeah, but one is growth and one is decay. Yeah, that's why decay is negative. So this is the way the book does it. I will write that, and I don't need to write out my version. My version has K being negative, and then you don't need the negative, and it simplifies your life somehow. I don't know how. Maybe it doesn't. Here, stuff is growing and growing and growing, and if you have two people, they can have a certain amount of babies. But then you have more babies, and so now you can have more babies than you had before, right? We talked about this with rabbits. And so things grow exponentially because every new thing is contributing some increase power, increase ability to the function. Here, what you have is there's a certain proportion of your stuff that's going to just vanish into thin air. It's going to decay, it's going away. And the rate at which it vanishes corresponds to how much stuff there is left. In the same way that the rate at which your population increases depends on how big your population is. If you have 1,000 rabbits, your population increases at a certain rate, a certain number of rabbits. The rate might be the same. It might be the same K. But how many rabbits do you get in a month if you have 1,000 rabbits? Well, some number. How many rabbits do you get after a month if you have 10,000 rabbits? Well, 10 times the number. And so the number of rabbits depends on how many rabbits you have. Here, the amount of stuff you have left depends on how much stuff you started with. So what is this idea of exponential decay? So I am not I was going to say rocket scientist. I'm not a rocket scientist. That has nothing to do with this. I am not a physicist. I am especially not a nuclear physicist. So you could take other classes. You could take a class in physics. Chemistry will even talk about this. The bottom few rows of your periodic table are radioactive elements, and radioactive elements are interesting because they are wobbly, right? They're funny. There's something a little wrong with them, and what they do, the thing that makes them interesting, is that they decay, they break up, they fall apart. And the way they fall apart is actually kind of statistical. If you have one atom of a radioactive material, you don't know when it's going to fall apart. You don't know when it's going to decay. What happens when it decays? It throws off some subatomic particle, maybe a neutron, maybe an electron, maybe a something. I don't know. Do I look like a nuclear physicist? I think we've already established I'm not. But it throws off something depending on what it is. And then it turns into something else. It becomes a different element. And so you can read about that if you want to somewhere else. You could ask me and I'll say, yep, turns into a different element. Well, like, give me an example. What does radioactive iodine turn into? How about uranium? Yeah, it turns into something else. I want to say, yeah, whatever I say would be wrong. I should look it up. You don't know what's going to happen if you have one molecule of uranium. But if you have 100 molecules, well, that's still not very much uranium. Let's say you had 100 grams of uranium. Well, there's some decay rate. And so your uranium, it'll decay. And you cannot predict which particle it will be, but some particles over time will decay. And if you wait long enough, so much has decayed that only half of it is left. And that time is called the half-life, time after which only half the original material. And you think, well, it still weighs the same. It will be very close, but it's turned into something else, right? Your 100 grams of uranium is now, after the half-life, 50 grams of uranium and something else. Half of the original material remains. Original material, of course, that's P sub 0, right? So I told you before that you do need to memorize this doubling time formula. T equals the ln of 2 over K, and yeah, make a story out of it. If it has gorillas in it, so much the better. I apologize, you also have to memorize the half-life formula. And again, it's a special time. It's the time after which there's half of the stuff. And you have to memorize this formula, so pay attention. Oh, Gary, you trickster. Yes, it's exactly the same formula. Well, how can it? Yep, it's exactly the same formula. The derivation's in the book if you need to see it. Or, yeah, there's another version. And yeah, they're exactly the same. If you only want to memorize one, memorize this one. And then if you need this one, well, it's algebra. You know, multiply both sides by k. Oh, then the k goes away and there's a k over here. Divide both sides by t. Oh, the t goes away, so you're left with the k and the t's on the bottom. These are exactly the same formula. If you know the half-life of plutonium, you could figure out what its decay rate was. And if you knew the decay rate of californium, there's one, then you could find the half-life. And so that's how that works. The most interesting application they have, and they'll give you some, right? They'll give you some problems where you'll have a little table and they'll list 5 or 6 different elements, and they'll give you K and you plug it in and you write in T, or they'll give you T and you plug it in and you get K. And mostly you're using your calculator and not much brains. It's kind of sad. The problems are always more interesting when you can think about it. So this stuff has been going on for a long time. Nobody really noticed it until there was this French-Polish woman. Maybe she was a Polish-French woman. I don't know. She was French and Polish, named Marie Curie, right? She was the first woman to ever win a Nobel Prize. Oh, that's kind of nice. And she did a lot of experiments with radium, and then died of cancer, right? They didn't realize that radiation hurts you some. So that's kind of interesting. Let's do something even more interesting. I've got to draw the sun. Here's the sun. Cute, huh? And I've got to draw a grassy field. That's grass. And I've got to draw, this is my favorite part, a cow. I can't really draw. I'm just doing this for fun. I guess it has a tail, doesn't it? And then it's got like stuff here. Yeah, stuff. I don't know what a cow looks like. Cow looks something like this. It's a cow. I'll put horns on it so you know it's a cow and not a horse. He's a very happy cow. Does that look anything like a cow? It's a Guernsey. Yeah, oh, I see. It's a cow. Yeah, okay. Got it. Cow. What's the point of all this? The point of all this is there are up here nitrogen. There's nitrogen in the atmosphere. You can tell it's nitrogen because it has little ends on it if you look at it with a microscope. Maybe not. And what happens is there are cosmic rays. Ooh, cosmic rays. Cosmic rays coming from the sun. Doo, doo, doo. Cue the theremin, right? There's cosmic rays, and what happens when a cosmic ray hits a nitrogen molecule, and this doesn't happen very often, but you know, once in a while, then the nitrogen molecule magically changes into carbon-14. They usually put the 14 up above. So when struck by cosmic rays, this sounds like Bruce Banner, right? You're thinking gamma rays turned him into the Hulk. When struck by cosmic rays, sounds kind of like I'm making it up, doesn't it? Nitrogen. I'm glad you find this interesting. I think this is a very, very interesting. This is one of my favorite lectures of the whole course. Nitrogen changes, and a lot of people don't know about this. Changes to carbon-14, and we write carbon-14 like this. It's a big C, that stands for carbon, and then there's a little 14 up and to the left. This one almost looks better. This almost looks like 14C. No, the 14 has to be up in the air, which happens to be radioactive. Well, that's fine, Gary. I'm not sure we care yet. This carbon-14 combines with oxygen, ordinary plain old oxygen, to form radioactive
Carbon dioxide, CO2. Do you remember your old stuff? This is why I drew the grass. See, look, grass, grass. There's a certain known percentage proportion, you could use either word, of the CO2 in the atmosphere that is radioactive. And then what do you know? Who breathes carbon dioxide? And you say, well, not me. Actually, I do. I breathe it out, but I don't breathe it in. The plants breathe it in. Plants breathe in CO2 and turn it into stuff. You know what the stuff is, right? Carbohydrates, that's right. Because carbon, where are they getting the hydrate part? Well, they drink stuff too. Plants breathe in CO2 and turn it into carbohydrates. So there is a certain known percentage of a plant that is radioactive. So far, so good. Then what happens? I didn't draw the cow just for fun. The cow has to eat the grass. Yep. The cow eats the grass, the radioactive grass. And if you wanted to, you could do this. What did I say? Turn it into carbohydrates. Yeah, the cow eats the radioactive grass and turns it into radioactive meat and skin and bones and hair. Yeah. So there is a certain known percentage, I say this a lot, of a cow that is radioactive. Have you ever eaten a cow, anybody? I know people that have. Have you ever eaten any grass? No, I don't mean those brownies. I mean, have you ever eaten any plant? I'm using grass as my example. Grass. But it's the same with broccoli and cauliflower and beans and corn and rice and everything you've ever eaten. And you think, yeah, but I don't like plants. I'm more of a carnivore than a, well, okay, the cow, okay, it's still, well, what is this known percentage? Well, it's, ask a scientist. That's fine. But then what about the plant, certain known percentage? It's exactly the same percentage. Because the plant is breathing in the CO2. That's what it turns into. It's exactly the same percentage. And then the cow, it's exactly the same percentage. Kind of interesting. Well, let's go on to the next slide. Yeah, I get to draw a cow. What's your favorite part of the algebra class? Well, I get to draw a cow. It comes about week 12 or so. You get to draw what? Why? Because of this story. Yeah, okay. A sad day befalls us. A sad day. The plant dies. What happens? No more breathing. What does that mean? That means no more new radioactive carbon dioxide. We know that the plant's radioactive because, it's a plant. Radioactive carbon, the carbon-14, radioactive carbon-14 decays over time. So less of the plant after a while. We actually know. And similarly for the cow, right? A cow, every cow on Earth, every human on Earth, every plant on Earth, right now that's alive has the exact same proportion of radioactive carbon in it. There is carbon in you. There's a lot of things in you that are made of carbon because you're an organic creature. And there is a certain proportion of that carbon in you that is radioactive. It's the exact same proportion as what's in the atmosphere. When the plant dies, when the cow dies, when you die, the radioactive carbon will start to decay. And after a while, there will be less of your carbon, less of the cow's carbon, less of the plant's carbon that is radioactive. We actually know, what do we actually know? That the half-life for carbon-14 is 5,750 years. That's the number the book uses. That's not exactly right. We'll talk about that in a second. So if we found an old plant, papyrus, that's a plant. What do people do with papyrus? They lay it out in a grid form and they pound it with a hammer, and they make a writing material out of it. The ancient Egyptians did this. The ancient Romans did this. The ancient Greeks did this. The ancient Indians didn't do this because, papyrus grows in Egypt, so why would they? No, they use palm leaves and stuff, like a papyrus scroll. If we found an old plant, like a papyrus scroll, that had only half of the usual percentage of radioactive carbon in it, then we would know that scroll, or that wooden tool handle, or that leather bowstring, or anything that was once a plant or an animal. A bone, right? You find a bone, bones have carbon in them. You think, well, bones are calcium. There's more calcium in your bones than anywhere else in your body. But bones aren't mostly calcium. Bones are mostly carbon. Yeah. And you wait a while and then you see, hey, what's the percentage? What's the proportion of radioactive carbon in this bone? Half as much as usual. Oh, then it's 5,750 years old. Only a fourth as much as usual. Oh, well, then it lost half. Now it's half. And then it lost another half. Now it's fourth. So double this, 11,500 years old. Well, this one only has an eighth. And you think, yeah, but what if it's not a half? What if it's like it's lost 20%? Well, you have a formula. P of t equals p sub 0 e to the negative kt. Oh, yeah. Oh, I can figure out. Oh, I know what T is, because you know what K is, because you plug this in, ln of 2 over 5,750. Now you know the decay rate K for carbon. We would know that scroll is 5,750 years old. And we call this is carbon dating. You've heard of it. Sometimes they call it radiocarbon dating, or they'll call it carbon-14 dating. But carbon dating, invented by University of Chicago chemist. University of Chicago, I've been to their chemistry department. I was in their building. Nice place. Invented by a University of Chicago chemist. You probably want to know his name, Walter Libby, who in 1960 received, it was a good idea. Don't you think this is a clever thing? I mean, I'm impressed. When a human being figures out something like this, I just kind of get excited. There's a little shiver goes up my spine. This is like cool stuff. He got the Nobel Prize for it. Yeah, he figured this out. And it's been used ever since, right? The latest big example that you've heard of the Shroud of Turin, right? And so this is a burial cloth. It's a linen cloth. And you say, linen? Well, what's linen made out of? Flax, right? Linen. It's, it's a plant. Yeah, it's flax. Yeah, if you have a piece of cloth, well, where else is cloth going to come from? Well, what if it's not from a plant? What if it's from a sheep? Maybe it's a wool cloth. Okay, and what does the sheep eat? Oh yeah, grass. Never mind. Yeah, this works for any living creature, every living creature on Earth. After a while, it doesn't work as well. If something's 50,000 years old, it becomes harder to measure. It's a really small amount of radioactive carbon. There are also other issues. It's a destructive process, right? What they do is they burn it, but they're getting better and better and better at it, and the amount of material they need is smaller and smaller and smaller. So I mentioned the Shroud of Turin. It comes from Turin, Italy. And it has interesting marks on it, as though it were a burial cloth of someone. And people, not me, but people say this is the burial cloth of Jesus, right? Jesus of Nazareth, who was put to death, a couple thousand years ago. Not quite. And then strange things happened, right? You've heard the stories. And this cloth has these odd markings. And so, yeah, you can tell this is, I don't want to destroy anyone's faith, but when they did the radiocarbon dating, they found it was not quite that old. Yeah. So too bad. It'd be neat if it came out to be exactly that old. But the Dead Sea Scrolls, the book gives an example. Example 5 talks about the Dead Sea Scrolls, which some of them were wrapped in linen, right? And so linen, plant, very easy to do. Those are the oldest biblical manuscripts we know of. Yeah, they're very, very old. And they figured out the age with carbon dating. There's a fellow in Indiana that was dredging a creek. Great discovery. I like telling the story. Just think, in 1,000 years, someone could analyze your bones or your skin or whatever it is you have, assuming there's something left of you, and they could tell how old you are. You could just leave a note if you wanted. Most of the people, it's not like the people with the Dead Sea Scrolls said, by the way, I'm writing this on a Tuesday, and then I'm putting it in this earthenware jar on a Wednesday, and no, we don't know. It's interesting stuff, the whole community. But that's a different class. That would be an anthropology class or a history of religion class. In 1970, Amos Flora of Flora, Indiana, that sounds suspicious to me. Is this a true story? Discovered teeth and jaw bones while dredging a creek. It's like, whoa, look at this. Hey, Fred, doesn't this rock look like teeth to you? Yeah, and that looks like a jawbone. Scientists discovered that the bones were from a mastodon. Ooh, how interesting. Don't you wish you were dredging a creek in your backyard and you found a mastodon? They had lost 77.2% of their carbon-14. Bones lost 77.2% of their carbon-14. How old are they? Well, this is really, really cool. So we need to know some stuff. We know the half-life of carbon-14 is T equals 5,750 years. Oh, so here's the deal. You might say to yourself, well, this is fine. We know this, but how do you know that the proportion of carbon-14 in the atmosphere has been the same for the last 50,000 years? As you said, it comes from cosmic rays. Yes, Mr. Skeptic, I said it comes from cosmic rays. Well, you think the sun's the same, there's sunspots, and sometimes there's more cosmic rays and sometimes there's less. Well, yes, Mr. Skeptic, that's true. And so there's different amounts of carbon-14 in the atmosphere at different times, aren't there? Well, yeah. And so you don't know the proportion. Actually, we do. It's like, wait, what? Yeah, we do. This is such a cool story. And the way they do it is we have trees, and if you have trees, and if you actually have the tree, well, you have tree rings. And so there are trees that we can tell how old they are. And then you notice the growth patterns, right? Because the rings aren't like ring, 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 ring. It's like fat ring, another fat ring, kind of a thin ring, and then two more fat ones, and then like six thin ones, and then a fat one. And because what? Weather is different. If you have two different trees that coexisted, you can line up their pattern of rings, the fat and the thin, and the fat, fat, thin, thin, thin. And then you can date this tree. Oh, we know this tree lived at the same time. So anyway, they've done this for thousands and thousands of years. I mean, tens of thousands of years. We actually know. And so the scientists, when they do this, we're going to do the simple way. We're going to say 77.2%, we're done. The scientists, they know that, yeah, actually, this is a more complicated formula. Because we do know the changing over the years percentage. And it's a very, very small change, but gosh, it gives you a lot more accuracy. So anyway, we know this, so we know. So the rate of decay is K equals the ln of 2 over T, which is the ln of 2 over 5,750, which is some number. I don't care what it is. I'm going to use my calculator anyway. Why should I do it now? And we know. So how much is there now? What proportion is there? And this is the tricky part. Well, it's 77.2%. Nope, that's how much it lost. Okay, minus. At the beginning, there was 100% of the radioactivity, and now there's less radioactivity. E to the, I'm supposed to put a negative there because I'm doing it the book way. E to the negative natural logarithm of 2 over 5,750 times T. And so we say, you divide all this stuff out, right? And you say 0.2 228, does that feel right to everybody? Equals e to the negative ln of 2 over 5,750 t. We take the natural logarithm of both sides, and what happens? All this stuff drops down. Put that in your calculator, see if you get 12,320. And that's how you do a carbon dating problem. And they like those. They're kind of fun. They're kind of interesting. They have another one with an Egyptian mummy. King Tut. Yeah. Because what's his sarcophagus made out of? Sarcophagus, that's like we would call it a casket, right? Casket. Yeah, that's a good word for it. Sarcophagus. It sounds fancier, doesn't it? Sarkos means flesh and phagos means eat. A sarcophagus is a flesh eater. You put the body inside. Yeah, it eats the body. And it comes from the Greek. Years, I better put the units, huh? Good. That's how you do them. They're kind of fun. Think of this half-life formula. If you have a very high, a very long half-life, so the stuff stays around for a long, long time, then you're dividing by a large number, and that means you have a pretty small rate of decay. And if you have a very short half-life, you have a very high rate of decay. And some things, there are half-lives that are in the microseconds. I mean, crazy, crazy fast things that they last for a split second, and literally a split second. You blink your eye and your stuff is gone. It's decayed into something else. And then you have other things that last for 20,000 years before half of it's gone. And it becomes an issue because some of those things that last 20,000 years are produced by our nuclear power plants. And so people who are against nuclear power, one of the reasons is they're concerned about radioactive material lasting for a long, long time, and what are we going to do with it? And that's kind of a good question. The stuff that decays faster, it decays faster because it's throwing out more particles. And so that's the stuff you don't want to be close to. You don't want to inhale it or ingest it accidentally. And the stuff that lasts a long, long time, well, you still don't want to get close to it if there's a lot of it, but it's not throwing off a lot of particles. In a certain sense, it's more dangerous because it lasts longer, and so you have potentially more exposure. But it's also less dangerous that you can be close to it and you won't get very, very sick. So there you go. I'm not a doctor either. Don't quote me on any of this. Oh, no, there's one more thing I got to show you. This is on page 368. I'm going to write down page 368 because I'm not going to show it to you. You can read it. Models of limited growth. It's a page and a half because you're thinking this exponential growth thing, P of t equals P sub 0 e to the kt. It doesn't really work, does it? And no, it doesn't. And the reason is eventually you run out of food, right? You run out of food. Well, I haven't run out of food yet. Well, you'll run out of space. There's a thing in the news today about Boise and how the house prices, home prices have just skyrocketed, and they continue to skyrocket. And the reason is Boise is a nice place and everybody's moving here. And so we have this growth, and eventually we will run out of space. And our lovely mayor is very concerned that people who aren't rich aren't going to be able to afford a house or to be able to rent an apartment. And that's might be a concern. Well, fortunately, growth usually is limited because you run out of space. You run out of food. And so there's a formula for that, and they give it to you. And there's one exercise in the homework that requires you to know it. So you can read that, and I think you'll understand it fine. I don't think there's an issue. And it won't be on the test, I'll tell you that. I don't put logistic growth. It's called logistic growth. Yeah, there you go. So we're done with chapter 6. Did I say 6? We're done with chapter 5.